In the previous videos, I explained that analytic functions are functions that can be written as power series. In this video, I will summarize everything you need to know about analytic functions and the tool we use to prove a function is analytic, the remainder theorems. Fair warning, this video is fully packed with theorems, some quite technical which I won't prove. They will make the rest of this playlist easier, and we will get lots of nice and useful applications of Taylor series, so they are worth it. So far, I have been casually saying that a function is analytic when it equals its Taylor series, but that is not precise enough. I need to specify which Taylor series, and I need to specify on which domain. So to begin, let's write a more precise definition. I start with a C-infinity function f on an open interval I. I require C-infinity so that at least we can write its Taylor series. Now, let's fix a point A in the domain, and let us call S sub A the Taylor series of f centered at A. I will say that f is analytic at A when... I want to say when f of x equals S sub A of x, but for which values of x? For all values of x in some open interval centered at A. In other words, this means that the function and the Taylor series of the function centered at A are equal near A. That was the definition of analytic at A. If instead I say that f is analytic, and I do not specify a point, it means that f is analytic at all points in its domain. That's it. That is the precise definition of analytic, which we often carelessly summarize as the function equals its Taylor series. Here are some results about analytic functions which I'm not going to prove. First, polynomials are analytic. They are finite power series. Second, sums, products, quotients, as long as we don't divide by zero, and compositions of analytic functions are all analytic. Moreover, the derivatives and antiderivatives of analytic functions are also analytic. In short, all common operations with analytic functions produce analytic functions. But there is more. An analytic function is written as a power series, and we know that in the interior of the interval of convergence, a power series can be manipulated like a polynomial. So, all the operations above can be performed with Taylor series the same way we would perform them with polynomials. And finally, we know that the Taylor series of a function at a point is unique. Thanks to all these properties, my goal now is very humble. I just need to prove that the exponential and the sine function are analytic. That's all. Why only these two functions? Because all other elementary functions can be written in terms of these two functions, polynomials, and the operations I listed. Moreover, once I know these two are analytic, getting the Taylor series of new functions will be easy by manipulating the Taylor series I know. I will illustrate how to do this with examples in a video linked in the description. Okay then, how do I prove that the function is analytic? Let's review the notation and make a plan. Let f be a function defined on an open interval I, and let a be a point on I. If the function is Cn, then we can write the nth Taylor polynomial. As you know, it is given by this sum. We can always write the function as the nth Taylor polynomial plus the nth remainder. The remainder is just the difference, the error we make when we approximate the function by the polynomial. If the function is C∞, then we can write the Taylor series. As you know, it is given by this infinite sum. We also know that the Taylor series is the limit of the nth Taylor polynomials as n approaches infinity. This is because the Taylor polynomials are the partial sums corresponding to the Taylor series. Finally, the function is analytic when, in addition, the function equals the Taylor series. In other words, analytic means that the error made when using the Taylor series as an approximation is 0. Now, the Taylor series is the limit of the Taylor polynomials, therefore the error made when using the Taylor series as an approximation is the limit of the remainder of the Taylor polynomials. In other words, being analytic is equivalent to saying that the limit of the nth remainders, as n approaches infinity, must be 0. This is what we need to prove in order to show that a function is analytic. You may be thinking, haven't we already established this? Don't we already know that the limit of the remainders is 0? Let's be careful. There are two important limits involving the remainders. What we knew from the very definition of Taylor polynomial is that if I fix n, the order of the Taylor polynomial, and then I make x approach a, then the error approaches 0, and it approaches 0 fast. That is what we knew. But in order to prove that a function is analytic, I need to look at a different limit. I need to fix x, and then I need to take the limit as n approaches infinity of the remainder, and I need that limit to be 0. Okay then, to prove the limit of the remainders is 0, it will help to estimate the remainders. There is a perfect tool for this purpose, the Remainder Theorems. I say theorems in plural because they are a family of theorems. They are all very similar. A typical Remainder Theorem has this form. If some hypotheses are true, then we get some formula for the remainder. There are at least 3 common versions of the Remainder Theorem: Lagrange's form, Cauchy's form, and the integral form. They each give a different looking formula, but for our purposes they are interchangeable. They all allow us to estimate the remainders and to prove that functions are analytic. I won't write a proof for any of them, but I will mention that all their proofs use the mean value theorem or perhaps Rolle's theorem. This would not be a surprise. Every important theorem in calculus relies on the mean value theorem. As an example, here is the precise statement of Lagrange's Remainder Theorem. Once again, this is just one of the versions. This is not more or less important than the others. Let I be an open interval, let A be a point in I, let n be a natural number, and let f be a Cn+1 function. Notice that we only need f to be Cn in order to write the nth Taylor polynomial, but we need f to be Cn+1 in order to get this formula for the nth remainder. Here's the formula for the nth Taylor polynomial that you know, and the nth remainder is defined as the difference between the function and the polynomial. Then, under these assumptions, we get this new equation. It is very close to being the n plus first term in the Taylor series, but instead of evaluating at a, we evaluate at xi. What is this new variable xi? I have to introduce it, otherwise the statement is meaningless. The theorem says that there exists a number xi between a and x such that this equation is true. In a way, this is reminiscent of the mean value theorem. The mean value theorem says that, under certain hypotheses, there exists a number c that satisfies an equation. This theorem says that, under certain hypotheses, there exists a number xi that satisfies another equation. Okay, how is this theorem useful? First, we can use this theorem to prove that a function is analytic. That was the motivation we had throughout the video. I will illustrate this with an example in a later video. Second, we can also use this theorem to estimate the value of a complicated function with a Taylor polynomial. An estimation is only useful when we can bound the error, and this theorem allows me to do exactly that. I will also illustrate this with an example in a later video. Both videos are linked in the description. And this is everything you need to know about analytic functions and the remainder theorems.